So Ting-Yu Chen, aka NiNi, is a security researcher at DevCore focusing on vulnerability research and reverse engineering. He won the title of the Master of Pawn at Pwn2Own Toronto 2022 with the DevCore team and made achievements in CTF competitions. His talk is focusing on network infrastructure, so a comprehensive review on the less traveled road, 9 years of overlooked MikroTik Pre-Auth RCE. Thank you.
Hi,
the floor
everyone.
is yours.
Hi, everyone. Today is a talk about 9 years of overlooking MikroTik Pre-Auth RCE. And I am NiNi Chen. I'm currently a security researcher at DevCore, and we are from Taiwan. I'm also a member of Belgian CTF team and member of Undefined. So, why? Why the RouterOS? Because we want to participate in the Pwn2Own Toronto 2022 as one of the target, the router board of MikroTik hasn't been pwned in the previous event. So we want to try it. Because if your target is the difficult one, then there is less chance you have a block collision, right? So you may already know the rules. Participants must find a pre-auth RCE with no user interaction to acquire the point. And a special category, so-host mashup, was introduced in 2022. Participants have to chain a router's WAN vulnerability to another device exploits to earn the points and bounty. The bounty and point in this category is relatively high. So it's a good target for us to earn more money and win the game. We started to survey the possibility to finding a pre-auth RCE on router board. Let's recap some backtesting quickly. The router board of MikroTik is quite popular, and the RouterOS is the operating system of router board hardware. By scanning the MikroTik, we can observe about 3 million devices online. RouterOS is a standalone operating system based on Linux kernel. And MikroTik also offers ISO image, so we can run it as VM. It's closed source code and closed ecosystem, but it did use some open source code, so it is affected by the GPL. But according to the download terms on MikroTik's webpage, you have to pay $45 to get a CD with GPL source. Nice try. But if you want to participate in Pwn2Own this year, I suggest you not to get the GPL source code because someone had published it online on GitHub. But the code there is not really useful, so you just have to reverse by yourself. Currently, there are 2 versions of RouterOS, RouterOS v7 and RouterOS v6. That should be considered as 2 branches because their implementation are slightly different. And there is also something called cloud-hosted router. This is a RouterOS image for VM, but only the AMD 64 version is available. And our target is MIPS, so it's also useless. But you can try something on the VM. It's also. And most services on RouterOS are implemented by MikroTik itself because it's closed ecosystem. And they share a similar architecture. So we name this kind of binary Nova binary afterward. And they use Nova message to talk to each other. The RouterOS is based on the Linux kernel, but the customer is actually trapped in a customized CLI. So you can access the underlying Linux system. Only the developers can install a kind of backdoor package to access the Linux kernel for debugging purpose. And there is a special application called Winbox. This is a Windows GUI application. It's also a popular attack service. Because the Winbox interface on the router can be used to talk to other Nova binaries, and we'll talk about it later. So some of them can be accessed without authentication. It's also a popular attack service. To understand how people research the RouterOS, let's have a look at past CVEs of the RouterOS. There are a total of 80 CVEs, and 28 of these CVEs are pre-auth exploitable. And the victim is the router itself, not the client side. And 16 out of 28 are those in variant components. 8 out of 28 are DNS poisoning, allowing attacker to MITM or firewall evasion. Only 4 pre-auth vulnerability in history can lead to a shell or login as admin directly without user interaction. These are what we care about, but 3 out of 4 were found during 2017 to 2019, and the 3 out of 4 are in the wild. Let's have a close look, like CVE 2017-20149, aka Chimerate, is one of the exploits leaked from the CIA in 2017. By sending an HTTP request with crafted content length, like a very big content length, we can corrupt stack to execute arbitrary code by a special technique called stack clash. And the CVE 2018-7445 is a buffer overflow in SMB and was found by black box fuzzing. CVE 2018-14847 is also one of the exploits leaked from the CIA. This bug allowed an unauthenticated attacker to read arbitrary file on RouterOS. It sounds like it's not a big deal just reading the file, but since at that time the password stored in RouterOS was actually your raw password XOR with a known string, a known hash of a known string. So if you can read that file, you can recover a password very easily. And the CVE 2021-41987 is a heap buffer overflow in the function best64 decode of SCEP service. This was found on an APT C2 server. As we can see, these vulnerabilities are mostly in the wild. We can't really learn too much from them directly. So let's look at some talks. In 2017, there are 3 talks. They are about the package format adopted by the RouterOS, the developer backdoor, or how they store the password we just mentioned. They are helpful to have a big picture of RouterOS. And in 2018, the talk analyzed the Nova message, which was used by the Nova binary to talk to each other. In binary format and JSON format, it has 2 formats, and introduce how the Winbox client talked to the Winbox interface on the router by Nova message, and it found a post-auth overflow. In 2019, the talk, MikroTik, Firewall, and Net Bypass, is talk about the vulnerability in the Winbox. They can be used to scan the intranet if Winbox is exposed to the internet. The next, finding and exploit CVE 2018-7445. It found the stack buffer overflow in SMB we just mentioned. And the deep dive, MikroTik exploits a security analysis. It's about the CIA exploits and the massive exploits event based on the leaky payload. The next one, help me, vulnerability, you are my only hope. Release a tool to help users to jailbreak their device to check if the leaked exploit we just mentioned were already compromising them, because you can access the underlying Linux system to check if you were compromised, so you have to jailbreak. And the last one, RouterOS chain to root, it's about chaining DNS poisoning vulnerability and the downgrade attack to get a shell. In 2022, pulling MikroTik into Limelight talks more about the Nova binary and disclose a post-auth vulnerability in www that can be used to jailbreak. And then also release a tool to help people quickly get a shell on AMD 64 version of RouterOS of the vulnerability. Yes, the tool is about the AMD 64. So if you are a participant of the Pong2On event, you want to debug your exploits, you have to write your own version based on this exploit. It seems like the whole world is talking about the Nova message in the IPC, right? So we also try to understand what it is. Let's talk about the IPC of RouterOS with an example. While a user login through the telnet to access the console of RouterOS is something like this. The telnet will immediately call execl to execute the login process to ask the user for user name and password. Then the login process will send a Nova message with username and password supplied to the user process to check if they are correct. The user process also responds in Nova message. It will send back an OK. The Nova message consists of key and value pair, and the key can only be numbers. The sys2 and the sysfrom are arrays contain the ID of the Nova binary and the ID of the handler. We'll talk about later, which should handle this message. The communication between two processes is actually something like this. Every message is sent to the loader via socket, and the loader dispatches the message to the corresponding binary. So, assuming that the ID of the process on the left-hand side is 1039, the ID of the user process on the right-hand side is 13, and the handler 4 is responsible for checking the username and password for login, right? The login process sends a request with username and password to the user process. The value of the sys2 means the target. So the sys2 is handler 4 of the binary ID with 13. Next, the loader removes the target binary ID in sys2, adds the source binary ID to sysfrom, and then forward the message to the target process. When the user process receives the message from the socket, it will also remove the handle ID from sys2 and pass it to the corresponding handler. Then the handler do the rest of things about the user authentication. We mentioned that the Winbox interface on the router is a popular attack surface. That's because the protocol Winbox client, which is on Windows, is a WinGUI. To talk the interface on the router is a Nova message in the TCP packet. So if the target handler fails to check the sender's privilege, that can cause problems, right? Like an unauthenticated user can send a Nova message through the loader to arbitrary binary if they didn't check the permission by themselves. The loader won't check that. The message used in IPC is constructed by the env message and relative function. Nova message is typic key value mapping and can contain various types, and also another Nova message so it can be nested. Because the JSON format of the Nova message is deprecated, so we only talk about the binary format today. The M2 at the beginning of the Nova message is the magic bytes, so let's skip it. Then it uses 4 bytes to describe a key. The first 3 bytes of key are ID. The last bytes is type, and the bytes following are the value of that key. So the message's ID, types, and value looks like this. Type like bool, like boolean, type like boolean, can be expressed with 1 bit directly. So it just uses the lower bit of the type bytes. To understand which binary corresponding to the ID, in the sys2 or sys-from, we need to pass a special file format called x3. It's under the loader directory. It's a kind of XML, but in binary format. If the binary was, so it's something look like this. The ID of the bin user is 13. Okay, you have to write a parser to pass the x3. And if the binary was introduced by installing a package, because it's a closed ecosystem, so you can still install some package, but from MikroTik. If the binary was introduced by installing a packet, its ID is under the loader directory of that packet. But some IDs can be found in the x3 file because the process is not persistent. The ID is just a serial number, like the login process we just mentioned. Because you spawn a login process every time a user wants to log in, so it's actually just a serial number. Other binaries also have their own x3 files for different purposes. For example, the x3 file of www describe which URI should be handled by which servlet. It seems like it's a good target for fuzzing, right? Because it's compact and the key can only be numbers. But we can't just fuzz it and expect it we get something after two months because we need RCE, not a crash. This is a spoiler, okay? While we were writing our exploit with the vulnerability we found later, there is a talk at POC 2022. It's called MikroTik RouterOS Security, the forgotten IPC message. Though, I think it's far from forgotten because when you look back the previous page of the slides, you will find that most research are actually playing about the Nova message, so it's never forgotten. But anyway, the talk is about fuzzing the Nova message. It turns out a lot of post-CVEs, which is red here, are found by the fuzzing, by that talk. By the number of CVE, it looks like the fuzzer has been running for a long time. The smaller ID is like CVE 2020 and 20211. It has been fuzzing for like 2 years. And a bit of afterthought, I don't think we can get a better result if we would do the same thing. Not to mention, we only have 2 months. So, is it still possible to pwn the RouterOS? It looks like it's super hard. Reviewing these CVEs again, most of the vulnerability we think interesting were discovered many years ago. Researchers also found lots of vulnerability. But as we can see, the MikroTik becomes safer and safer. But somehow, in 2021, a vulnerability in SCEP server was discovered by analyzing an exploit on apt-c2 server. So, was it undiscovered until then because it was not a default feature? Or is it just because people have overlooked something? Most of the talk and article focus on jailbreaking, analyzing the in the wild exploits and the Nova message in IPC. I have a summary after reading this article and starting to reversing by ourselves. That is, no one with sanity would like to dive into the detail of Nova binary because it's secure by obscure. It's really hard to reversing, and the code base is huge. So, where to start? I don't think the system is perfect now. There is a gap between researchers and attackers. So, what was missed if we want to find some pre-auth RCE bug in RouterOS? The first question is, where are the entry points of the customized IPC, which is the Nova message we just mentioned? Most of them can only be accessed by authenticated users. We can foresee that playing with the Nova message in IPC will result in lots of post-auth bugs. IPC is just a part of implementation of most of the functionality. We want to review the crucial part directly and carefully. For example, how does the DHCP process parse a DHCP package to extract the info it needs? Then we have to mention the architecture of the Nova binary. Every Nova binary has a looper. The looper uses poll to check the status of sockets and process event in each loop. It's just like a regular event loop if you have seen everywhere, just like a game loop or something. Looper is responsible for communication between the current process and the loader. The looper registers a special callback for the Unix socket, which is used to communicate with loader. The special callback here is on message sock. Will dispatch the message to the corresponding handler once it receives Nova message from the socket. So how does the handler works? While the looper receives a Nova message, it will dispatch it to the corresponding handler and look at the right-hand side. If the sys2 only specifies the binary ID, the looper will handle the message. Otherwise, 0 is for handler 0, 1 is for handler 1. Let's assume the handler 1 is responsible for Nova message this time. And then it will call a function in vtable with the cmd prefix, that corresponding to the command specified by the syscmd. Like if the command is in syscmd is shut down, it will call the cmd shutdown. It's something like that. And because the handler is base class, so command related to object are unimplemented. The cmd unknown is often overridden and used to extend the customized command. But sometimes the developers of MikroTik just want to override the handler CMD instead of the CMD unknown. So you may have already read some of this in the past research. Someone has talked this about. But most of the time, the Nova binary use the derived classes rather than the base class. The derived class can store a collection of objects of a specific type. For example, while the user is setting up a DHCP server, they will send a message to handler 0 of the DHCP process to create a DHCP server. The handler 0, which is an instance of AMAP, is a derived class of handle class. It will call a function on its vtable with offset hex 7c to create a DHCP server object and insert it into a tree. So it's something like an STL of the C++, right? The hex 7c is the offset to the constructor of the inner object. And you can find the offset of such function in other derived classes by reversing their command add object, this function. You can find the constructor, offset of constructor. In the previous example, the web panel sent a Nova message to DHCP to create a DHCP server. But what if I told you that some functionality don't even use the Nova binary? So if you keep playing with the Nova message or fast with the Nova message, you won't find this attack service because they never use it. Take the CDP and LLDP for example. The CDP is something like Cisco Discovery Protocol. And they are implemented in the Discover, which is a process called Discover. The looper registers 2 callback functions, one for CDP, one for LLDP. The looper keeps looping and checks the status of the socket. If there are incoming packets, the looper calls the callback function. The callback of CDP will extract the information from the packet and store them directly into another ASEC map without sending any normal message. So we want to explore such case that never use a normal message. So maybe there'll be some vulnerability hiding there wasn't found by fuzzing. So we start to review the RouterOS by enumerating functionality and reversing them based on the concept we just mentioned. Then we found something strange. Okay, actually, this part was nothing about the reversing. One day, while plugging and unplugging some cables connect to the router, suddenly, the log file showed the RA-DVD crash several times just by plugging and unplugging my cable. So we tried to reproduce the crash by manually plugging and unplugging cables about 1,000 times. But we couldn't figure out the crash condition. The condition is unknown, and the crash appeared randomly. Okay. Instead of mindless unplugging and plugging the cables, we try to reverse the RA-DVD to see if we can find something interesting. We didn't find the root cause, but we got something better. What is RA-DVD? RA-DVD is a service about the SLAAC of IPv6. Let's say a computer or a node wants to get an IPv6 address. It will firstly communicate a router solicitation to all routers, ask for network prefix. Then if a router receives the RS, it will multicast a router advertisement with network prefix to all nodes. Now, a node can calculate its own IPv6 address by combining the network prefix and the UI64. And UI64, which is calculated from the MAC address. Another scenario is that if an upstream router A, maybe it's an ISP, they give you a prefix with /48, which assigned in advance by email or something. Then you can use them whatever you want in your LAN. Then here comes the link prefix and router prefix. First, the router B acts as a node on the interface that links to the router A. So now it's an SLAAC client. The router B asks a router A for a prefix. The router A sends a /64 prefix for router B to calculate its own IPv6 address. Router B calculates an IPv6 address, let's say it's 2001 DBA 1, and use it as the interface that links to the router A. So now the router A can route all traffic to the address under /48 to router B. Now when nodes want to get IPv6 and send the RS to router B, the router B just multicasts the /48 prefix to the nodes as usual. Then the nodes acts as usual. The function of the RA-DVD in RouterOS should have two functionality. The first one is it can act as a node to receive RA, and the second one is it can multicast RA to the LAN, right? So let's follow the execution flow of RA-DVD to find the bug. The RA-DVD has a similar design pattern to the discover process we just mentioned. So we call them Nova binary because they share similar architecture. The looper pulls the socket in every loop, and if there is incoming ICMPv6, it just calls the registered callback function. What callback function do is roughly like this. It checks if the packet is a valid RA or a valid RS. If it's a RA, then store information in handler 1. If it's an RS, they just multicast RA. But there are actually 3 cases the RouterOS will multicast the prefix to node. The first is when it receives the RS from the nodes. It's simple, right? But the second is when it receives an RA from the upstream router. The last one is the router will multicast prefix in the default period, which is in 200 to 600 seconds. But the problem is we actually can't find the broadcast behavior when it receives the RA in first glance. It's actually about the subscription mechanism we'll talk about later, but we didn't know that then. But the other two cases can be traced directly. The RA DVD calls send RA right after it receives an RS. The handler 1 registers a timer to send RA periodically, so we can find the send RA function by tracing these two methods. Following the send RA function, we found something interesting. While the RA DVD deals with the DNS advisory, it will advise DNS to nodes based on the DNS list it received from upstream. The add DNS function is used to flatten the DNS tree and add it to the ICMPv6 packet. The RA row is the ICMPv6 payload, which is a local variable with a size of 496 bytes. Okay. Step into the add DNS, and we can immediately find out there is probably a stack buffer overflow. The function adds DNS to packets by MEM copy without any boundary check. That causes a stack buffer overflow in the DNS if the DNS is big enough. But the problem is the max length of RDNSS of an RA is 8 bits, which is insufficient to override the return address. It can even cause a buffer overflow. But if the RA packet was not the first one sent to the RouterOS, the RA DVD have to expire old RDNSS. That makes the RDNSS flatten another tree to overflow more bytes for us. So if it will expire the old one, so it will flatten 2 trees. So now what we have to do is we have to act as a bad neighbor that send a router advertisement with a big RDNSS list to the target router. Then send another router advertisement with a big RDNSS list. Now the return address is overwritten with an IPv6 address in the RDNSS of the first RA. So we can override the return address by some IPv6 address in the first RA. It's time to construct the exploit, and it looks very easy because there is no protection enabled. And on the MIPS, there is no NX bit because the hardware didn't support that. So you can easily execute your shellcode. So let's just find a way to jump on the stack and run our shellcode. That should be really easy, right? Like CTF 101. The overflow IPv6 address are sorted since they were stored in a tree. To make the order of the IP address stable and ensure the shellcode is good, we can use part of IPv6 prefix as a serial number and put a jump at the end of each address to jump over the prefix because they are not a valid instruction. But because of the delay slot of MIPS, which means the instruction after the branch instruction will always be executed before the branch instruction itself. We have to move the jump instruction forward But the other problem is that you cannot do the syscall in the delay slot. So basically, this is a bad idea. Oh, it's another CTF 101 problem. Just make the prefix a valid instruction that won't affect our gadget or shellcode, then everything is fine. And because we didn't leak any stack address, plus we didn't find any gadget, they can be used to move stack pointer from register. So what we did here is first write our gadget on memory, then jump to that gadget. Finally, our shellcode will be executed. Sounds good, but there is iCache. The MIPS CPU has two caches, the instruction caches and data caches. While writing our gadget on memory, we are actually writing on Dcache. Now, when we try to control the execution flow to execute the gadget for running our shellcode, the process first checks if the instructions are already in the iCache. But because we wrote our gadget on the data section, the cache always misses, so that the memory content will be loaded into the iCache. That causes the processor to execute a bunch of nodes until the program crashes. To flush the Dcache, we need to make the processor context switch or exhaust the Dcache, which size is 32 kilobytes. There is no sleep in the RADVD. Other functions would also trap into the kernel, but they don't guarantee the context switch would always happen. To make our exploit constantly successful in maximizing the chance to win the game, we have to flush the 32 kilobytes Dcache. Luckily, the value in randomized VA space of RouterOS is 1, which means the heap is not randomized. The only thing we need to do is do some memory allocation to extend the heap and write some garbage on it. We may run out of bytes for shellcode because of that. But the DNS addresses were stored in a tree we just mentioned that costs a lot of memory space. The heap is already larger than 32 kilobytes during processing a request. So we can call the MEM copy by GOT hijack to write 32 kilobyte garbage on heap to flush the Dcache for our shellcode directly without any memory allocation to consume more bytes for our shellcode. And the profit. The vulnerability was assigned CVE 2023-32156, and it's already being fixed. After that, we found the vulnerable code has existed at least since RouterOS v6. This means the vulnerability has existed since 2013, 9 years until we found it, and 10 years until they fixed it. So, no one with sanity would like to dive into the detail of non-binary. QED, you're welcome. Combine the exploit with our another exploit for Canon printer for point-to-on. The attacking scenario is that an attacker is a bad neighbor of the MikroTik router, sending crafted ICMPv6 to attack the router. And if we compromise in the router successfully, we can forward our payload to attack the printer behind the router. The whole setup can be simplified as such in context. We can almost see our 100K bounty. But there is another but. Our exploit only working on Mac OS and fail on Ubuntu, whether it's a VM or not. And the host of the point-to-on, they run Ubuntu VM. So we have to make it successful on Ubuntu VM. We try to debug the exploit by running the exploit on Mac and recording the traffic, replay, and fail, right? We also dump the traffic from Ubuntu and replay it on Mac, then it's success. What? So we guess there is an OS reorder the packet. It must be like that. So we put a sniffer on the router to monitor the traffic from Mac and Ubuntu. And because the AF packet is not affected by any firewall chance, the result should be reliable. But let's just look the same. The last result could be that I have to go to Toronto in person along with my laptop, but we can't leave it like that. Who knows if this bug will suddenly happen again during the contest, even on Mac OS, right? Eventually, we found the problem. It's all about speed. The gap looks tiny, and you may never notice that on Wireshark. But the difference between them is actually 390 times. The problem is not on Ubuntu. It's just because the Mac sent two packages too quickly, caused some rest condition. And we didn't actually calculate how many bytes we need. We just put some garbage and do some pattern matching, just like everyone does. So we fixed that, and we got some, and the probability of success is almost 100%. Okay, now the problem is, where's the rest condition? Maybe we can use this bug for another entry of the point-to-one event. Then we got more money, right? The problem is, the RADVD is only one thread. How could there be a rest condition? I didn't mention that while the RADVD parsing the incoming packet, the DNS address are stored in a vector. But somehow, the handler passed a DNS tree to the addDNS function. What's the relationship of these two members? It's actually about why we can't find whether the callback function multicasts the RA when it receives an RA packet. Let's look closely at the callback function. There is an array responsible for storing something called a remote object. Then it looks straightforward. Just iter the new DNS vector and do mvrodns on each of them, and append result to the DNS remote object vector. So what is the remote object? The remote object is a mechanism to store common resource in the process, and the other process can access them via ID. For example, a DNS remote object is stored in the handler 2 of the resolver, and the RADVD only preserves the ID of object in handler 1. Now, let's talk about the subscription in the Nova binary. The binary IP pool 6 is responsible, for example, the binary IP pool 6 is responsible for managing the IPv6 address pool. The DHCP subscribes to it so that the DHCP can react to the change. It's done by sending subscribe Nova message. And the sys notify CMD can specify which command you want to subscribe. For example, the hex FEOOB means notification. So if there is another binary, try to add an object to the handler 1 of the IP pool 6 by sending a Nova message. The add object of handler 1 will be executed. In the most case, the add object will call send notifies to notify subscribers who subscribe to hex FEOOB to inform them that the IP pool 6 has changed. So when the RADVD receives RA from the upstream of the router, like the corner, right? To create equals or RODNS to create DNS remote object for each IPv6 addresses in the RDNSS of RA. The command add object of handler 4 is right-hand side. In the resolver, is responsible for such a request and will add the IPv6 object into the handler 2. Also, because the handler 1 of RADVD subscribes to the resolver's handler 2, the handler 2 will notify it with every DNS addresses it has now. So the handler 1 constructs the RA for LAN with these DNS addresses and broadcast them. The problem is in the implementation of RODNS. The send Nova message by post message, which is non-blocking. It means the remote object won't get the object ID immediately. So if we send request too fast, the second RA arrives before the RADVD get the object ID of the old remote object. The RADVD can only soft delete those old objects rather than really delete them. They cause the rest condition. This is what happens if we follow them step by step. Because both processes are single thread, let's assume they are in the first loop of the looper, while the RADVD receives the first RA from when with one DNS address. The RADVD creates a remote object in the resolver by sending a Nova message. And the resolver will set up a timer after receiving a first request because it cannot tell how many aiding operations should be grouped. So it just set a timer and send only one notification when time is up. Apart from notification, resolver should send a response back to tell the RADVD the object ID of the remote object it just asked for. Here, it should send back the object ID it asked for. But if we send a second RA quickly before the resolver sends the object ID back, the RADVD can only mark the old DNS remote object as destroyed, that is, soft delete. Then keep going to creating the DNS remote object for our DNSS in the second RA. That will send a request to the resolver, but as I say, we send the second RA too quickly. The resolver is still in the first loop, which try to send the object ID it created in the first loop back to RADVD. So our request will stay in the socket. Then keep going. Sorry. Now the resolver send the object ID back. The response handler, a callback register by the first request, will handle the response. The handler finds out the object has already been marked as soft delete, so it won't update the object ID. Rather, it will post another request to the resolver to delete that object. The request will be processed in the third loop of the resolver after the request of creating the DNS remote object for the second RA. In the second loop of the resolver, it processes the creation request with the DNS address from the second RA and responds with object ID. So, now time's up. Okay. The timer of the resolver thinks a group of aiding operations should have been done. And it's time to notify everyone what DNS address he has now. And because the handler 1 of our RADVD subscribes to the handler 2 of the resolver, it receives the DNS address in the Nova message, then broadcasts them in the LAN. At the moment, the result of 2 requests is missing. That's why our first version of exploit can only work on macOS, because we trigger the rest condition. It mixes the result of 2 requests into one. So the pattern of the rest condition in remote object is as following. First is it uses non-blocking method to create delete remote object, and the target process subscribes to the remote object. Then we can mix the result of 2 requests into one. That may make us bypass some check in binary, So we try to find another vulnerability with this pattern, so we could register the lane category of the router in pwn to earn more money and points. But we ran out of time and did not manage to find other vulnerability to exploit the lane side of the RouterOS. At least, we are the first team to exploit the Soho Smash Up. There are actually one team before us to exploit the Soho Smash Up, but they failed. We succeed, yeah. And we also won the title of the Master of Pong. So let's go to summary. Summary, MikroTik re-implemented everything with its own design IPC. So the business logic is scattered all over to to find the critical code for reversing, you have to have an abstract concept of Nova binary. And there is a pre-auth RCE on WAN that exists for 9 years. Also, we introduced a pattern of race condition in remote object due to non-blocking method to you. So if you want to participate in this year's pwn event, you may try this direction. And the last thing, we drop tools we use in we will drop tools that we use in pwn event to erase the work to reversing the RouterOS at GitHub, and we will do that. Okay, so I think reversing something is very critical to find such bug, especially when there's a lot of work already against this target. But by reversing, you always got the raw data, and you know where to look rather than other people to find the hiding bug. So today, this is my talk today. And any question?
Question? No?
No question?
Okay.
So thank you for the talk. It was very nice, and I learned lots about RouterOS from your talk, so great. I had just one question. Did you use a jailbreak version of RouterOS while doing your research, so you could also debug what's happening, or did you just went pure reverse engineering and like trying to guess what was happening and crafting your exploit out of like no debugging environments?
While finding the vulnerability, we do statically reversing. But after that, we do dynamic debugging by using the bug from the pulling the MikroTik into line blind from the, what's that? I forgot the name of the company. But yes, margin research.
Okay, thank you.
Yeah.
Other questions? No? Okay. Well, thank you.
Yay.
Thank you again.